Good day, students. We are now on a new topic, Topic 3, Lesson 1, Points of Concurrency, Part 1. So in Part 1, we're going to look at two different types of points of concurrency. That is the circumcenter and incenter. We're really going to be focusing on how these points of concurrency are created and what relationships that they have within triangles. So let's look at the first one. The first example here says that we're going to prove the perpendicular bisector theorem. So in this proof, they give us lines L, M, and N are the perpendicular bisectors of the sides of the triangle AB, AC, and BC respectively. And we have P as the intersection of lines L, M, and N. We are trying to prove that the distance from P to A, which is a vertice, from P to B, another vertice, and from P to C, another vertice, are equal to each other. So as we mentioned in our warm-up activity, we know that P would be our circumcenter. And we know it's a circumcenter because the circumcenter is created by three perpendicular bisectors. And those perpendicular bisectors bisect all three of the sides of the triangle. So statement number 1 states that, and we know that is given because that obviously is stated in the proof here. We also know that P is the intersection of all of the lines that are stated here for L, M, and N, and that is also given in our problem here. So let's look at statement number 3. Statement number 3 states that PA, which is located here, is equal to another segment because P is on the perpendicular bisector of AB. So let's think about this. Let's go back to perpendicular bisectors. The perpendicular bisector of side AB is located on line L, and line L is here. So if P is on that perpendicular bisector, what do we know to be true? Well, from P to A, we know that's equally distant from P to B, and P to B is located here. So we know that P is equally distant from the endpoints of the side of this triangle because it's on the perpendicular bisector. So PA would be equal to PB. Let's look at statement number 4. So let me clear this off so we can look at the second statement, or statement number 4. So statement number 4 says, some segment is equal to PC because P lies on the perpendicular bisector of BC. So once again, we have P as our circumcenter, or our point that's on the perpendicular bisector, and we're looking for side BC. So the perpendicular bisector of side BC would be line M, line M. So line M is here, and P is on that perpendicular bisector. So remember, any point on the perpendicular bisector is equally distant from the endpoints of the segment that it bisects. So from P to C, which is located here, would also have to be equally distant from P to B, which is located here. So that means that these two segments are equally distant from the point that's on the perpendicular bisector. So PC would be equally distant, or equal to PB. So the last statement is what we're trying to prove. Okay? So we see that PA, we notice from statement number 3, PA is equal to PB. And from statement number 4, we see PB is equal to PC. But what reason would make this to be true? Well, if in statement number 3, we see the first statement has PB in it, and from statement number 4, we see the second statement has PB in it, that means that these two statements share PB. If I have two statements that share the same part, that means that the outside part of that statement also has to be equal as well. That tells me that the reason that PA is equal to PB is equal to PC is through the transitive property of equality. So now we've proven why the circumcenter of P, erase all this, why the circumcenter of P is equally distant to all of the vertices of the triangle, which proves the perpendicular bisector theorem. Okay, so in example 2, we're going to actually use this perpendicular bisector theorem and the circumcenter to show and apply why this is true. So example number 2, part A says they give us that from Z to G is 65, from H to L is 63, and from Z to L is 16. And we are trying to find from H to J, this segment right here, and from Z to J, this segment here. Okay, so we know we're dealing with perpendicular bisectors, and we have 3 of them here. And when we have 3 perpendicular bisectors, it creates a circumcenter, which is Z. So let's start out with HJ first. So from Z to L, that is the perpendicular bisector of side HJ. We know it's perpendicular because we have this sign indicated here that a 90-degree angle is created between the 2 segments. So if that is true, we know that L here is the midpoint of HJ. If L is the midpoint of HJ, that means that H to L and J to L are equally distant from the midpoint. So if HL is 63, that means LJ is also 63. So to find HJ, we know we have to take 2 times the distance of HL. So 2 times the distance of HL means that we're taking 2 times 63, and 2 times 63, we know that is equal to 126. So that means the full length of HL is 126. Okay, so now that we've found HJ, let's focus on ZJ. So ZJ is here, right? Z to J is the distance from the circumcenter to one of the vertexes of the triangle. Well, what do we know about the theorem that we just did in the proof? We know that from the circumcenter of Z, it is equally distant to all of the vertices of a triangle. So that means from Z to J, that's equal to the distance from Z to H, which is equal to the distance from Z to G. So we can write this statement, ZJ is equal to ZH, which is equal to ZG. Well, in the problem, they gave us that ZG is equal to 65. So if all of these 3 segments are equal, that means ZJ is also equal to 65. So we found HJ as being 126 and ZJ being 65. Let's move on to part B, which is another example of using the perpendicular bisectors and the circumcenter theorem. So in this problem, they give us from Z to M is 25, from Z to H is 65, and from G to J, this full entire segment here is 120. In this problem, we're trying to find from G to M, and we're also trying to find from Z to G. So let's start with G to M first. So once again, Z is our circumcenter, and we know from Z to M is a perpendicular bisector because of this marking that we have here. So that means that M is our midpoint of segment GJ. So if GJ has a midpoint of M, that means that it's cutting this segment into 2 equal parts. So G to M is equally distant as from J to M. So that means if I'm trying to find GM, I know that GM is going to be half the length of GJ. We know that GJ is 120, and half of 120 is 60. So that means that both of these parts are 60. All right, so let's look at ZG. ZG, from Z to G, we know that is the distance from the circumcenter to the vertex of one of the vertexes of the triangle. And what do we know about the distance from the vertex to the circumcenter of a triangle? Well, we know that it is going to be equidistant to all of the distances from the vertex to the circumcenter. So that means that from Z to G is the same distance as from Z to H, which is the same as from Z to J. But in the problem, it told me that ZH was 65. 65. So from Z to H is 65. That means all of the distances that were stated here are 65. So what we're trying to find is ZG, and ZG we know is also 65. So we found JM as being 60 and ZG as being 65. Okay, example 3, we're talking about angle bisectors of triangles. So here in part A, we're trying to find the measure of segment BC, which is located here. So from this example, I see that angle CAD has been bisected into two congruent parts based on the markings that we have. So we have the measure of angle CAB, and that's equal to the measure of angle DAB. I also see that we have point B here that is attached to segment BC and segment BD, which are perpendicular bisectors to the rays AC and AD. So if I notice that ray AB is a bisector of this angle CAD, and I see that B is equally distant, B is on the perpendicular bisector of BC and BD, I can conclude that from B to C is the same distance as from B to D. So that means I can set up an equation of saying BC is equal to BD. And this is going to help me find the length of BC. So BC we know is 6y minus 16, and BD is 4y plus 6. So now we're just solving for y. So I'm subtracting for y, subtracting for y, and that gives me 2y minus 16 equals 6. I add 16 to both sides, so that gives me 2y equals 22. Divide 2 on both sides, so y equals 11. So remember, we're not trying to find the value of y, we're actually trying to find the value of BC. BC we know is 6y, which is 11, minus 16. So 6 times 11 gives me 66, minus 16 gives me 50. So I know segment BC is 50. But how do I know for sure it's 50? Well, we know that BC and BD are the same measure, so I can plug in y, 11 for y, into BD, and I get 4 times 11 plus 6. 4 times 11 is 44 plus 6 is 50. So I see that these two measures are the same, so that tells me that BC is in fact 50. Let's look at part B. So part B, once again, we're still dealing with the angle bisector theorem, but at this time we're trying to find the measure of an angle. We're trying to find angle JKL. So once again, JKL is a part of a bisector of JKM. So JKL and MKL are two equal angles. I also see that KL includes point L, which is equally distant from the two rays KJ and KM. Because they're equally distant from the two rays, I know that the measure of angle J, KL, is equal to the measure of angle MKL. And that would tell me that L would be considered my N center. So now that I have my setup, I can now substitute the values. 2x plus 1 is JKL, and 3x minus 9 is the measure of angle MKL. Now I can just solve. Subtract 2x, subtract 2x. So I have 1 equals x minus 9. I add 9 to both sides. So 10 equals x, which is really x equals 10. So remember, we're not trying to find the value of x. We're trying to find the value of the measure of angle JKL, which equals 2 times x, which is 10, plus 1. So that tells me the measure of angle JKL is 21 degrees. 2 times 10 is 20, plus 1 is 21. But how do I know for sure that this is 21 degrees? Well, I can check the measure of angle MKL, which is 3 times x, which is 10, minus 9. So I have 30 minus 9 gives me 21 degrees. I see that's the same as the measure of angle JKL. So that concludes that these two angles are in fact congruent. All right, let's look at our last example, which is example number 4, part A. So it tells us here that we have JV, which is located here, and that is an angle bisector, and KV is also an angle bisector. Let's clean this up. So these two segments are angle bisectors. As you can see, we are trying to find the distance from point V to side KL. So we're trying to find this distance here. Well, it says here V is the end center of triangle JKL. We know it's the end center because we just identified two angle bisectors here, which was JV, and here, which was KV. So by the end center theorem, we know V is equidistant from the sides of JKL. So that means from V to side KL is the same distance as from V to side JL as from V to side JK. The distance from V to side JK we already see is 7.3. So that means the distance from V to KL is also 7.3 based on the end center theorem. Let's look at part B. Part B, same exact question. We know that JV is an angle bisector and KV is an angle bisector. We've already concluded that it bisects this angle into two equal parts and this angle into two equal parts. We are trying to find the missing angle of VKL, this angle right here. So let's start off with what we know. JK bisects angle KJL. KJL, this full angle here. So we know KJL is split into two equal parts, and we see here that one of the parts is 19 degrees. So that means if VJL is 19 degrees, this other part right here, KJV, would also have to be 19 degrees. So if I wanted to find the full measure of JKL, I would have to take 19 degrees and multiply it by 2, which gives me 38 degrees. So that means the full angle right here of KJL is 38 degrees. So if I know this full angle is 38 degrees, and this full angle right here that has been identified, let's put that in a different color. This angle right here of JLK is 106 degrees, That means I can use the triangle sum theorem to find out the full measure of this last angle here, JKL. So I'm going to add 38 degrees plus 106 degrees, add it with the last angle JKL, and equal that to 180. Well, 38 and 106 gives me 144 degrees. And to find the missing angle, I'm going to subtract 144 degrees from both sides. So subtract 144 degrees. And that leaves me with JKL as 36 degrees. So the full measure of this angle is 36 degrees. But remember, we're not trying to find the full angle of JKL. We're trying to find this little piece here. Remember, the little piece that we're trying to find is this angle right here of VKL. Well, I already know that the full measure of the angle is 36, and VKL is a piece of that angle. It's been bisected, so that means it's half of it, half of 36. And half of 36 we know to be 18 degrees. So this little angle right here we know is 18 degrees. Well, ladies and gentlemen, that has concluded our lesson for today for topic 3, lesson 1. Please make sure you're going to your warm-up activity and watching the videos and your OneNote class notebook to review the vocabulary terms. Good day, students, and I will see you in class.